Hey everyone, you ready to dive into something really mind-bending?
I'm ready.
All right, excellent. So today we're going deep on string theory.
Yeah.
It's this, super ambitious attempt to try to explain, well, everything in the universe.
Well,
All the forces, all the particles,
yeah.
the whole
The
shebang.
whole cosmic
Yeah,
shebang.
exactly. And we're working from this scientific paper that really walks us through the history
Okay.
and all the major concepts
Yeah.
of string theory. And believe me, there are some serious aha moments waiting for you.
I believe it. You know what's really interesting to me is that string theory, it didn't actually start out with this like grand goal of unifying the universe.
Right.
Its origins were a lot more focused.
Okay.
It was really about trying to make sense of the strong nuclear force,
Uh-huh.
the one that holds the nucleus of an atom together.
Right, right. It's amazing how something that starts so specific can end up, having such huge implications, right?
Yeah, absolutely.
So remind me, like, what was the state of physics back then?
Okay, so back in the 1960s, physicists were they were really struggling
Okay.
to like understand how particles interacted
Yeah.
within an atom.
Mm-hmm.
And so they came up with this mathematical expression called the
Mm-hmm.
Veneziano formula.
Okay.
And this formula described particles scattering beautifully.
Right.
But here's the catch.
Okay.
They didn't actually understand what the formula was really telling them.
Okay.
They had the answer, but not the question.
It's like having the answer, but you don't know the question.
Exactly.
Okay.
So how did they crack the code?
Yeah. How did they crack the code?
Well, that's where things get really, really interesting.
Okay.
It turns out that this formula,
Uh-huh.
it wasn't actually describing these like point-like particles at all.
Okay.
Instead, it was describing the behavior of tiny vibrating strings.
Oh, wow.
Yeah, it was like a total surprise.
Okay.
Like finding a hidden message in,
Oh, like a secret code.
yeah, in a song you've heard 1,000 times.
Oh.
Yeah.
So are you saying, like, instead of picturing particles as, like, these tiny little dots,
Yeah,
we should think about them as these tiny vibrating strings?
that's exactly right.
And the way they vibrate is what determines what kind of particle it is.
Yes.
Like, one vibration for an electron, another for a quark.
That's the heart of it. But
Okay.
there were, of course, some kinks to work out.
Okay.
You know, this early version of string theory, it definitely had some quirks.
All right.
Like, for one thing, it needed 26 dimensions to work,
Oh, yeah.
which is a bit mind-boggling for us humans who only experience 4.
26 dimensions is a little much to wrap my head around, I gotta say.
Yeah, it is.
What else?
What else was going on?
Well, it also predicted the existence of this crazy particle
Okay.
called a tachyon.
All right.
And this tachyon could theoretically travel faster than light.
Right.
And that is like a huge no-no.
Yeah, that's a
In Einstein's universe, it breaks like all the rules.
right. To make matters worse, it didn't even include fermions,
Oh, no.
the building blocks of matter.
Right.
You know, the stuff that makes up you and me.
Right.
Not very unifying if it leaves out most of the universe, is it?
It's not a great theory of everything if it doesn't have everything.
Exactly.
Yeah.
So it sounds like they had a lot of work to do.
So how did they resolve those problems?
Well, this is where supersymmetry comes in.
Okay.
This incredibly elegant idea that that says every known particle has a hidden partner,
Okay.
a super partner
Uh-huh.
with different properties.
Okay.
Think of it this way. Supersymmetry is like a whole hidden world
Wow.
of particles that are mirroring our own,
Oh, wow.
right? And not only does this solve some of those pesky theoretical problems,
Okay.
you know, like those extra dimensions
Yeah.
and those pesky tachyons,
Right. Right.
but it also opens up these exciting new avenues
Okay.
for discovering new physics
Oh,
at the Large Hadron Collider.
cool. So every electron has a secret, like, super electron buddy.
That's the idea.
That's wild.
That's pretty wild. But if they started out just trying to explain this one force, you know, the
Mhm.
strong force,
Yeah.
how did string theory all of a sudden become a candidate for a theory of everything?
Right. That's a good question.
Well, that's where string theory makes a prediction.
Okay.
That is so unexpected.
Okay.
It totally changes the game.
All right.
You see, string theory predicts this very specific particle,
Okay.
a massless
Okay.
spin 2 particle
Uh-huh.
that just kind of emerges
Okay.
from the way these closed strings
Oh, okay.
vibrate.
All right. I'm following you so far.
Yeah.
What's so special about that particular particle?
It turns out that particle matches the description of a graviton perfectly.
What's a graviton?
Oh, the force carrier.
Okay.
For gravity itself,
No way.
and no one expected it.
So they accidentally predicted gravity
They totally did.
just by playing around with these tiny little vibrating strings.
Yep.
That's incredible.
It really is. And it just totally transformed string theory.
Okay.
From a theory of the strong force to a potential theory of everything.
Wow.
And the surprises didn't stop there.
Okay.
So open strings, the ones with endpoints, right?
Okay.
Those naturally give rise to another type of particle,
All right.
gauge bosons.
Okay.
And guess what?
I don't know. Wow.
Those are the particles that are responsible for forces like electromagnetism and the weak force.
Oh, wow.
Suddenly they have this framework
Uh-huh.
that incorporates all the fundamental forces we know about.
That is seriously blowing my mind. But I gotta ask,
Yeah.
how does string theory tackle one of the biggest, like, conundrums in physics,
Okay.
unifying gravity
Yes.
with quantum mechanics?
Right.
These two seem like they just operate by totally different rule books.
You're telling me that's the million-dollar question in physics.
Mm.
And this is where string theory actually offers a potential solution. Okay, you see, Einstein's theory of gravity, general relativity,
Yeah.
it works beautifully on large scales,
Okay.
like planets,
Yeah.
stars,
Right.
galaxies.
Right.
But at these tiny scales, like the singularity at the center of a black hole,
Uh-huh.
it totally breaks down.
Okay.
We need this like quantum description of gravity
Right.
to understand what's happening there.
But so Einstein's theory is great for the big stuff,
Yep.
but not so much for the really, really tiny.
Yeah.
And this is where string theory comes in.
Exactly.
It fills in the gaps.
It does. And it does so in two very clever ways.
Okay.
So first, unlike these point-like particles, right?
Mm-hmm.
Strings have a finite size,
Okay.
okay, called the string length.
Okay.
Think of it as like a built-in minimum length,
Right.
okay, kind of safety net.
Okay.
And this size, it acts as a natural cutoff
Okay.
for all those infinities
Uh-huh.
that just plague quantum gravity calculations.
Okay, so that's one problem solved. What about the second?
Right. So second, the way strings interact is really constrained
Okay.
by the mathematical structure of the theory.
Yeah.
This leads to finite and calculable results,
Okay.
which is exactly what we need for a consistent quantum theory of gravity.
So no more mathematical infinities messing things up.
Exactly.
It sounds promising, but didn't you mention there were actually 5 different string theories?
Yeah, you have a good memory.
Well, it was just earlier.
It was. But it's not just one string theory. It's 5 consistent superstring theories,
Okay.
each with its own unique properties.
Okay.
So there's type I, type IIA, type IIB,
All right.
and then 2 versions of something called heterotic string theory.
Okay.
One with a gauge group of SO32,
All right.
and the other with an exotic E8 by E8 group.
Wow, those names are a mouthful.
They are. You'd think physicists would be happy with just one.
You'd think 1 would be enough. 5. It's like the universe has a sense of humor or something.
Yeah, it does.
Like it wants to keep us guessing. But why 5?
Why 5?
Yeah, why not just, one perfect theory?
Well, it was a puzzle for a while.
Okay. Yeah.
Why 5 seemingly different theories?
Yeah.
But later developments suggested that they might actually be different facets of a single, deeper, more fundamental theory.
Okay.
So imagine these 5 theories
Uh-huh.
as different projections
Okay.
of a higher dimensional object
Yeah.
that we can't quite perceive yet.
Oh, wow. So 5 theories, all potentially part of a single mind-blowing theory of everything?
That's the idea.
What else does string theory have up its sleeve?
Well, it introduces this whole new principle to physics
Okay.
called conformal invariance.
Right.
And it's a type of symmetry
Uh-huh.
related to scaling in angles.
Okay.
And here's where it gets really fascinating.
All right.
The requirement for this conformal invariance on the string world sheet, which is just a fancy name,
Okay.
for the two-dimensional surface, that the string traces out
Uh-huh.
as it vibrates through space-time,
Okay.
actually dictates the equations of motion in space-time.
Hold on. So you're saying that the rules of the game on this, like, 2-dimensional world sheet determine the laws of physics in our 4-dimensional space-time.
That's exactly what I'm saying.
That's like saying the shadows on a wall dictate what the object casting them looks like.
It is.
That's mind-blowing.
It's a mind-bending concept.
Yeah, It is. So we've gone from accidental origins to supersymmetry to a potential theory of everything to five-string theories to conformal invariance.
Yeah.
And I have a feeling we're just getting started.
Oh, you're absolutely right. The deeper we go, the stranger and more beautiful it gets.
Oh, I love it.
Yeah, and we got a lot more ground to cover.
All right, let's do it.
Okay. One of the most remarkable things about string theory,
Yeah.
is how it changes the way we think about gravity.
Okay.
It challenges this traditional notion
Uh-huh.
that space-time is this fundamental, unchanging background.
I'm trying to picture it. Can you elaborate on that a little?
Sure.
Like, what does string theory actually say about space-time?
So in classical physics, we picture space-time as this, fixed stage, right?
Yeah.
Where all the events of the universe are playing out.
Right.
But string theory suggests something way more radical.
Okay.
It suggests that space-time might actually emerge
Okay.
from the interactions of the strings themselves.
Whoa.
It's like the stage is built by the actors performing on it.
So instead of particles moving through a pre-existing space-time,
Yeah,
you're saying the strings themselves create space-time
that's right.
as they interact.
That's the idea.
That's a major paradigm shift.
It is.
Yeah.
And it leads to some, really mind-boggling consequences.
Okay.
For one, it opens up the possibility of extra dimensions
Oh, yeah.
beyond the, 3 spatial dimensions and 1 time dimension
Right.
that we experience.
You're right. We talked about those extra dimensions earlier.
Yeah.
String theory requires 10 dimensions to work.
That's right.
But if those extra dimensions are real,
Right.
where are they?
Where are they hiding?
Why can't we see them?
That's the big question.
Yeah.
One idea is that these extra dimensions are incredibly small,
Okay.
curled up at a scale far below our ability to detect them directly.
Okay.
So think of it like a garden hose.
Okay.
From a distance, it looks like a one-dimensional line,
Right.
but up close you see it has a second dimension
Right.
curled up in a circle.
Oh,
On that
okay. So these extra dimensions could be all around us, but just too tiny for us to notice.
Exactly.
It's like a whole hidden universe tucked away in the fabric of space-time.
That's right.
So what else does string theory have to say about space-time?
Well, it suggests that space-time itself is dynamic,
Okay.
that it can change shape.
Okay.
We already knew this to some extent from Einstein's theory of general relativity,
Right.
where gravity is described as the warping of space-time.
Right. Warping.
Yeah, and this warping is what causes planets to orbit stars,
Right.
for example.
Right. So massive objects warp space-time around them,
Yeah.
creating what we experience as gravity.
Exactly. But string theory takes this a step further.
Okay.
It predicts these fascinating objects called cosmic strings.
Okay.
Imagine incredibly dense, one-dimensional objects that can stretch across vast distances,
Okay.
warping space-time in these extreme ways.
Cosmic strings. That sounds like something straight out of science fiction.
It does.
What would these cosmic strings even be made of?
Uh,
Actual strings, like the ones we've been talking about?
well, not exactly the same kind of string,
Okay.
but they are one-dimensional objects
Okay.
that can have these profound effects on the structure of the universe.
Oh,
They could even be responsible for seeding the formation of galaxies in the early universe.
wow.
It's like they provide the scaffolding for the large-scale structure of the cosmos.
That's incredible. It's amazing to think that these theoretical objects, predicted by string theory, could have played such a fundamental role in shaping the universe as we know it.
Yeah, it's pretty wild.
But I'm still curious about those 5 different string theories.
Right.
How can we even test string theory if we have 5 different versions to work with?
That's one of the biggest challenges facing string theory today.
Yeah.
It's like having 5 different blueprints for a building,
Right.
but not knowing which one actually reflects reality.
Yeah.
It's kind of a head-scratcher.
Yeah, it is. So how do physicists even begin to narrow it down? What are they looking for?
So one way is to search for experimental signatures
Okay.
that could differentiate between them.
Okay.
For example, some string theories predict the existence of those super partner particles that we
Yeah.
talked about earlier.
Right, right,
We haven't seen them yet,
right.
but experiments at particle accelerators,
Uh-huh.
like the Large Hadron Collider,
Mhm.
are actively searching for them. Finding them would be a huge boost for string theory.
So finding those super partners would be like a smoking gun.
Yeah.
A piece of evidence that points towards the validity of string theory.
Exactly. It would lend credence to the idea of supersymmetry
Right.
and provide a much-needed connection between string theory and the real world.
It makes sense because, after all, string theory is still very much in the realm of theoretical physics.
Yeah,
It's incredibly elegant, it's beautiful,
it is.
but it needs some solid, like, experimental evidence to back it up.
Yeah,
Otherwise, it remains just a mathematical possibility,
well,
not necessarily a description of the real world.
you're absolutely right.
Yeah.
But even if we never directly detect strings or extra dimensions,
Yeah.
string theory has already had a profound impact on our understanding of physics.
Okay.
It's given us new insights into the nature of black holes,
Uh-huh.
the origin of the universe,
Right.
and the very fabric of reality itself.
That's a good point, yeah. It's really, like, influenced how we think about some of the biggest mysteries in physics.
Absolutely. And on top of that,
Yeah.
it's also pushed the boundaries of mathematics.
Okay.
It's led to the development of entire new fields of study.
Wow.
It's been this wellspring of new mathematical ideas and techniques.
So even if it doesn't turn out to be the ultimate theory of everything,
Yeah,
it's been incredibly fruitful,
it has.
both for physics and for
It
mathematics.
certainly has.
Yeah.
It's challenged our assumptions,
Yeah.
expanded our imaginations,
Mm-hmm.
and inspired countless scientists to push the boundaries of human knowledge.
That's true.
And who knows, maybe we're just one breakthrough away
Right.
from cracking the code of the universe.
It's like we're standing on the edge of a new frontier, looking out at a vast landscape of possibilities.
Indeed, the journey of scientific discovery is
Yeah.
full of unexpected twists and turns
Yeah, right.
and string theory with its, mind-bending concepts and audacious goals. Has
Yeah.
certainly taken us on a wild ride. It's amazing how we started with this, like, basic question about how particles interact,
Right.
and we ended up on this journey
Yeah.
exploring, the very fabric of reality.
It really is, it speaks to the power of scientific curiosity,
Yeah, it's a
doesn't it? Sometimes the most profound discoveries come from asking these seemingly simple questions.
absolutely.
And I think for me, one of the biggest mind-blowing revelations from all this
Yeah.
is this idea that gravity might not be a fundamental force at all.
It's a radical shift in perspective for sure.
It is.
In string theory, gravity just emerges
Yeah.
naturally
Uh,
from the interactions of these closed strings.
Right.
It's not something that's put in by hand,
Right.
like it is in Einstein's theory.
So instead of thinking of gravity as this, like, separate mysterious force,
Yeah,
we can view it as like a consequence of these tiny strings just doing their thing.
that's right.
It's like the universe is playing this cosmic symphony,
Yeah.
and gravity is just one of the instruments.
It's a beautiful way to put it.
And this idea of emergent phenomena,
Yeah.
it's not just limited to gravity either, right?
Right.
Scientists are finding that a lot of complex systems, from, flocks of birds
Yeah.
to financial markets,
Right.
they exhibit these, like, collective behaviors that you can't predict
Yeah.
just by looking at the individual parts.
It's like the whole is greater than the sum of its parts.
Exactly. Which makes you wonder,
Yeah.
what other secrets are, like, hidden in the fabric of reality,
Yeah.
just waiting for us to uncover them?
Right.
What other, like, seemingly fundamental aspects of our universe
Yeah.
might actually be these emergent properties?
It's a tantalizing thought.
It is.
And I think string theory, with its emphasis on interconnectedness and emergent properties, offers, like, a glimpse into those possibilities.
Yeah.
It suggests that there might be these deeper levels of reality with new rules, new laws
Yeah.
we haven't even begun to imagine.
It's this humbling reminder that we're still, like, at the very beginning of our quest to understand the universe.
We are.
Who knows what incredible discoveries await us in the future?
Right.
Maybe one day string theory, or at least something inspired by it,
Yeah.
will lead us to that, like, complete and unified picture of reality.
That's the dream.
It is.
It's a grand ambition,
Yeah.
that search for a theory of everything.
It is.
But even if that ultimate goal remains elusive,
Yeah,
the journey itself has been incredibly rewarding.
that's true.
I mean, string theory has challenged our assumptions,
Uh-huh.
expanded our imaginations,
Yeah.
inspired countless scientists to push the boundaries of human knowledge.
It really has, and it's, a testament to the power of human curiosity
Yeah,
and our drive to explore the unknown.
absolutely.
And on that note, I think we've reached the end of our deep dive into string theory for today.
Okay,
We've only scratched the surface of this
Yeah.
fascinating and complex subject.
we have.
But hopefully you've gained a new appreciation for the elegance
Yeah.
the beauty
A beauty.
and the just mind-boggling implications
For sure.
of this attempt to like unravel the deepest mysteries of the universe.
Okay.
If you're as intrigued as we are,
Yeah.
I really encourage you to delve deeper into this world.
I second that.
There are amazing books, documentaries,
Yeah.
articles out there
Tons of resources.
that explore the many facets of string theory.
Yeah.
And who knows, maybe one day you'll be the one to make the next breakthrough.
You never know.
In our understanding of the cosmos,
Right.
remember, the universe is this vast and mysterious place,
It is.
full of wonders waiting to be discovered.
For sure.
And that quest for knowledge,
Yeah.
like the vibration of a string, it can resonate through time and space,
That's beautiful.
inspiring generations to come.
It can.
So keep asking questions.
Yes.
Keep exploring and keep your mind open to the infinite possibilities.
Couldn't have said it better myself.
Until next time, keep exploring the universe.